Hi, my name is Mike Simons and I'm with Abode Energy Management. I want to welcome you all here today to talk about clean heating technologies in partnership with the City of Cambridge. I'm going to turn it over to Nikhil, and he's actually going to kick things off and talk about what the City of Cambridge is doing in relation to these types of technologies.
Thanks, Mike. Hi, everyone. My name is Nikhil Nadkarni. I'm an energy planner here at the City of Cambridge. I'm at 344 Broadway, the City Hall Annex building that you might be familiar with. I work on a number of our energy efficiency and clean energy programs here, which I'll touch on in just a second. But yeah, thanks for joining us today. Next slide, please. So Cambridge Energy Alliance is the city's program that we started a number of years ago to help residents and small businesses connect with energy efficiency opportunities and building upgrades, as well as clean energy like solar and clean energy from offsite sources. A lot of this fits into our net zero action plan. So in 2015, in response to a community movement and petition, the city adopted a net zero action plan that lays out how we can get to zero greenhouse gas emissions from our buildings, existing and new buildings, by mid-century. So it's a big lift. It's going to be a lot of energy efficiency. It's a lot of clean energy. And most important today, it's a lot of clean heat and decarbonizing how we get our heat. So to help our buildings and help our residents get towards these goals, we've created a number of programs over the years. So Sunny Cambridge is a program to help people connect with solar and has helped a lot of residents install solar on their roofs. We've been working a lot with renters, the Renter Efficiency Partnership. We have a community choice electricity program that lets people access clean electricity from New England renewable energy generators. And over the past few years, we've had a program to help our apartment and condo buildings implement energy efficiency and solar in a way that's designed especially for some of those more complex decision-making dynamics in a multifamily building. Next slide, please. So over the past couple of years, I would say starting in about 2017, 2018, we started getting more and more inquiries about clean heating solutions like heat pumps and solar hot water. People were interested in finding the right product because it's kind of a huge range of products out there and people weren't really sure about how to proceed. They wanted to make sure they're getting a qualified installer because there's a huge range of heat pump installers in Eastern Massachusetts. And there were a lot of incentive programs, but people wanted some help navigating those. So we wanted to respond to these inquiries in a well-informed manner and create a technical advising program that could help people out. And going back to those net zero goals, heating and cooling is over 50% of the energy used in Cambridge's buildings. So decarbonizing our heat and moving people to access options for clean heating and cooling is going to be an important part of our work going forward. So in 2019, we kicked off a pilot of Cambridge Clean Heat. And over the past year, we've been really excited to bring Abode on board. Mike and team have a lot of expertise in this field, and we're really excited to connect residents to all of the advice that they can provide. So going forward, we're also looking forward to expanding the program to work with building professionals, thinking about how they can incorporate clean heating into some of their project offerings, and to connect with home renovation projects because we feel that it might be a good intervention point to connect people to heat pumps and solar hot water when they're doing other work in the home. Makes things a little bit easier for everyone. So with that, I'll turn it over to Mike, and Mike, take it away.
Thanks, Nikhil. That was a great introduction. So just a little bit about the company, Abode Energy Management. The vast majority of the work that we're doing is related to either one of two things. So one, it's making sure that all of the home performance contractors in the Mass Save program are leading the customers in a path to a successful outcome. So we're making sure the energy audits as well as all the weatherization work meets the program's goals and expectations, and the customer is really satisfied with the work. After COVID, we pivoted and started doing a lot of work virtually as well, with supporting the Massachusetts contractors as well as contractors down in Connecticut to be able to run energy audits, whether in person, a hybrid visit, or over Zoom or a phone call like we're doing today. And then the other thing, we really do try and enrich the marketplace by always thinking about home performance first. So we are a BPI test center. I am a BPI proctor, BPI's Building Performance Institute. It's kind of the gold standard for helping people enter into the marketplace to be able to become an energy auditor or weatherization technician. So we support individuals who are interested in pursuing a path in clean and renewable energies. A little bit about me. Over the course of my professional career over the last 10 years, I ran over 1,000 energy auditors. I ran over 1,000 Mass Save energy audits. I trained over 100 Mass Save energy auditors. I've been a speaker at energy efficiency conferences, including Building Energy Boston here. And I'm a BPI proctor mentor, so I help people advance in that field. About me, I used to live in Cambridge. I'm about to be adopting ductless mini splits for my own home. I'm a little bit behind where I wanted to be. I was hoping to have them in already, but this spring, I will be the proud owner of 6 ductless units and 3 outdoor units. And I own a 100-year-old home. I have a steam boiler, a hydronic boiler, and there's plenty of energy efficiency work to be doing in it, but in the year of ownership, I've brought it really far along, and I'm happy to, try to, be in line to hit those kind of net zero goals by 2050. As far as the agenda for today, we're going to be talking about 3 different things. We're going to be talking about solar thermal, also referred to as solar hot water, air source heat pumps, and an opportunity to earn up to 6 CEUs for your Massachusetts CSL license. This deck is formatted kind of in a way of the types of questions that I hear and the typical answers that I would be providing. And I do think that that should be a really good primer for understanding all of these technologies. So why do we care about domestic hot water? Well, as Nikhil was saying earlier, about 50% of the home's energy use is related to heating as well as cooling. And we do see that in this chart over here. So this one has it at 59%. Right along with what's actually happening for the average home right now. But as we do start to really bring down that building's load by, sealing up the basement, continuous insulation along the walls, fully applied adhesive weather-resistant barriers, continued exterior insulation, hot roofs, spray foam, et cetera, that load is going to go down and down and down and down and down. But one of the loads inside of the home, it's not like one of the loads inside of the home isn't going to be moving, and that's traditionally domestic hot water. So right now a home may need, say 60 million BTUs over the course of the year for its heating load. After it's, headed in that net zero direction, that may be 20 million BTUs per year. But the domestic hot water load today, it's going to be 40 million BTUs. And when that home is net zero, unless there's less occupants in the home, it's still going to be 40 million BTUs. So at some point along this journey between today and 2050, every single home that we're needing to weatherize and improve, the domestic hot water load is going to end up being the highest load in the house. So it's just as important to be thinking about how are we going to be decarbonizing that load as well as everything else, all of the heating and cooling in the home. So it is important that this, that none of the equipment in your basement gets forgotten because it all is really impactful and there is really good solutions beginning with today. What are the different options on how to decarbonize your domestic hot water? Well, there's a lot of different types of domestic hot water. The traditional ones, we have like a tankless coil or an indirect storage tank, all tied to a traditional hydronic boiler. We also have standalone storage tanks. We have tankless storage tanks. There's a lot of different options, a lot of different configurations. Going into a New England basement, there could be venting issues, you know, if it's brownstones and you're attached. It could be that the domestic hot water heaters in the apartment, it really does get tricky. And that's why it is important to kind of think about all of the different possibilities for doing it. But the good news is there's really 3 different options today on the market. The traditional one is what's considered a heat pump hot water heater, also a hybrid one. In that type of a unit, it's just pretty much like the same technology you'd have on a window AC on top of a standard storage tank, and just takes the heat in the basement and it just dumps that energy into your domestic hot water, making it 130 degrees. They're typically relatively affordable, but sometimes you do need an upgrade on your main electrical panel. You need to deal with the condensate. And because it's all packaged together, there is a bit of a drawback that if the tank leaks, the heat pump's no good. If the heat pump breaks, the tank is no good. It's kind of an appliance where you're not, you know, there's really not too much service that could be happening to it. The other options is what we're focused on in the city of Cambridge, and they're both really good, and we'll be talking about them in just a minute. So how does it work and what are the options? So the 2 options that I'm talking about is a traditional solar thermal system. In New England, the type of technology on this, it's called a drain back. You know, at night, when the sun's not shining, there's no fluid inside of the panels. There's no fluid in any of the exterior piping. So there's no chance of any pipes freezing or bursting all year long. So the components are going to be the solar collectors that are up on the roof. And those are just going to be taking the radiation from the sun, transferring it into the panels, and then transferring that liquid into the storage tank, which is going to be heating up the hot water all spring, all summer, all winter, up past likely 120 degrees, and it's going to meet pretty much 100% of the load those 3 months of the year. However, in the winter time, when the sun's not shining, these panels aren't going to be producing that much, or if it's a very cloudy day, they're still going to be producing, but likely not nearly anywhere close to 100%. So anytime when you're thinking about this type of a traditional system, you are thinking about what am I going to be using to make up the rest of the energy. So most of these systems, they do have a electric coil built in, but some other types of systems can integrate seamlessly into an existing hydronic system. So if there's a boiler already in the basement, it's not mechanically complicated to add an additional zone onto that can make up the difference on this solar hot water system. There is 2 different types of collectors as well that are typically sold in New England. One's the flat plate. It's a little bit more seamless looking. It's a little bit more affordable, but does have a little bit less production. And then there's the evacuated tubes, which we're seeing at the bottom. Those are more efficient, a little bit more expensive. But if roof space is limited and you do want to produce as much solar hot water as possible, the evacuated tubes are a really good option. This product is super exciting. It's called a solar assisted heat pump hot water. And what this does, without any fans or motors to the outside, this is just going to be taking in heat from the outside, and whether that heat is radiation from the sun, it's radiation off of the trees, off of the ground, off of the snow. It's just going to be picking up all the different radiation that's going out and hitting that panel, and it's absorbing that, and then it transfers that heat and that energy to the indoor unit. It pressurizes the heck out of it, and it makes that refrigerant unbelievably hot. The water from your house passes over that unbelievably hot refrigerant. It gets up to 120 degrees, and then it sends that refrigerant back out to the outside. It drops the pressure and makes that panel extremely cold, and then it starts sucking that energy back into the panel and over and over and over again. And that's how like all heat pumps work. We'll talk about this a little bit more. But this is super exciting because the traditional heat pump hot water heater, it's in the basement and it's stealing heat from the surrounding air. And sometimes that is extremely favorable. Like if you're normally running a dehumidifier all year long down in the basement, that could be a favorable condition. But if you're interested in getting a decarbonized hot water heater, you don't have the roof space for a traditional solar thermal system, this is the perfect system. It has an it can use electricity as a backup, or alternatively, you can also be tying this in as an indirect storage tank as well to make up the difference. So how much does all of this cost? Well, the good news is we live in Massachusetts, and our state really is #1 in energy efficiency. So there's a lot of different programs to make these systems affordable. So with the traditional solar thermal system, when you do the federal tax credit, state tax credit, and alternative energy certificates, the AICs, it brings a solar hot water system pretty much down in line with what you would pay for a tankless on-demand system, like a gas tankless system. But the big benefits is you're not burning gas, you don't have any of the expensive venting costs, you don't need to run a gas line to it. And also, just from my experience running like 1,000 energy audits, a lot of people who do have that type of gas systems, there is minimum flow rates as far as gallons per minute. And it is, there is really a benefit for having a standard tank. All of your faucets, all of your dishwashers, all of your showers, everything will work just as it ever has. And if you've ever not had enough hot water, they can size up the tank accordingly. With the solar assisted heat pump hot water heater, once again, it qualifies for the Mass Save heat pump rebate. Because it's a solar panel, it does qualify for the 26% federal tax credit. And because there's kind of less complexity with the system, it's actually a bit more affordable. It's not as efficient traditionally as the standard rooftop panels, but it still does make a difference, and it is really a great technology for decarbonizing. And it's going to be here for the next like 30 years. So it'll bring us right to 2050, which is where we need to be. Okay, so that's everything that I wanted to talk about with solar thermal. Now I want to talk to you all about air source heat pumps. And I want to first start off with air source heat pumps is I cannot think about these systems without first thinking about design. And we'll be exploring this a little bit more throughout this presentation. So a lot of times when people are thinking about air source heat pumps and the technology that's readily available today, people are thinking about ductless mini splits. And let's just say, for example, that this home, it needed 3 tons worth of heating to supply 100% of the load on the coldest day of the year. If you just put a single ductless 3-ton unit into this home and you just turn it on, it's going to be fine. It's going to work just like a pellet stove would. It would work just like a wood stove would. Wood stove would. There's been people in New England for the last 300 years that have been heating their homes in this manner. The bedrooms are going to be colder. The living space is going to likely overheat in the winter time. But it works. There's nothing about this system that is wrong. It's just something that it will cause likely comfort issues. This is an alternative approach. And this is, I really have 4 rooms in here. I'm going to just put in 4 units. But the problem with this is, let's say that the load of the home is 3 tons. The smallest, it could be that let's pretend that the load, for example, on this home is actually 2 tons. The smallest outdoor unit that can handle 4 pieces of indoor equipment is 3 tons. So what ends up happening is this equipment because you wanted to put 4 units in, it's 1/3 the way oversized. And while this equipment modulates, it doesn't modulate like a traditional, say, gas boiler. This system may modulate to only 50% of its capacity. So what ends up happening is this system becomes oversized. It's turning on and off all year long. And the problem with that is, one, you're going to end up with an electric bill in the wintertime that's $600 or $800 for this home. And two, it would be no better today than just burning natural gas and adding those CO2 equivalent emissions onto the grid, because the coefficient of performance does take a significant hit when the system is oversized. So as we're thinking about this technology with Cambridge customers and talking to Cambridge contractors as well, is we're really just trying to promote getting the design just right. And to be able to do this is you're gonna need to start with the heat load, is figuring out exactly how much that room or those rooms, those zones, or those homes use, and then figure out how much equipment you're going to need to meet that number. So instead of putting in a unit in each and every bedroom or just having 1 unit for the entire house, this is really the approach that we're talking about. Let's just use 1 ductless unit to cover all the living space and then 1 ducted unit to cover the bedrooms. And this really does lead to these systems operating at the highest coefficient of performance. So how does a heat pump work? It works really well. Anytime that I'm on like Nextdoor, my community's Facebook group, I just always see these comments about people who are interested in heat pumps, and then on the thread, seeing the comments right underneath it, it was the best thing that I ever did. It's like every other day I see those types of comments. So how does a heat pump work? It works really good. How does it work technically? Well, there's like 2 building science things to keep in mind here. The first one is as you increase temperature equals increase pressure. So what that means is if you just increase the pressure on something, the temperature is going to increase. And if you decrease the pressure on something, the temperature is going to decrease. And the other building science principle that's really important is hot goes to cold. So this is how the system works. Say that it's 30 degrees outside. What we need to do is create refrigerant that's 0 degrees. And what will happen is that 30-degree energy in the outdoor air, it's going to migrate onto the 0-degree refrigerant that's inside of the system. As that refrigerant is at 0 degrees currently and it hits that 30-degree air and a fan is blowing over it, what's going to happen is that 0-degree refrigerant is eventually going to become 30 degrees, or it's going to be heading in that direction. So now that that refrigerant's picked up a lot of energy, it gets brought into the home through refrigerant lines, and it meets the indoor unit. The ductless mini split is what most people are thinking about. It's like a wall-hung air conditioner. But inside of that is a piece of equipment that what it does is it compresses the refrigerant. As it compresses it, it increases the pressure, which increases the temperature. So now this refrigerant is, let's say, 100 degrees. The indoor unit then takes air from the room, which is at 68 degrees. The 68-degree air passes over that 100-degree refrigerant, and it becomes 70-degree air, and then your house is comfortable. Now it just sends that refrigerant back outside, drops the pressure, refrigerant's back to 0 degrees, and it does it over and over and over and over again. And the cool thing about that is in a lot of, just slightly down south of here, the efficiency gain of using that type of technology versus just using electric resistance for heat, it improves it from like a coefficient of performance of 1 unit of electricity, 1 unit of heat, to a coefficient annually of around 3. So you put in 1 unit of electricity, you get in 3 units of heat, and it works really good. It's comparable in price to natural gas, and if sized correctly, it's about a 30 to 40% drop in emissions today compared to natural gas, and it's going to get cleaner and greener from there. What does a heat pump look like? It's a good question. There's a lot of different configurations. So the most common type of heat pumps that people think about in New England are ductless mini splits. And a ductless mini split can be mounted on a wall, it can be down on a floor, or it could be tucked right into a ceiling. Some of them in the ceiling are like 2 by 2, and then there's other ceiling cassettes that can fit right between framing that's 16 inches on center, and it provides a really nice seamless look. As we talked about just a few slides ago, there's also ducted mini splits. And those could be a discrete ducted system that's only serving 1 or 2 rooms. It could be a medium static unit where it's serving an entire floor, or it could be like a one-to-one swap out of a traditional furnace down in the basement. So you still have the same large ductwork going to every room in the home, and then kind of like a big central return down in the living space. So a lot of different flexibility, but each of these units that we just looked at, all of those can be tied to kind of that small briefcase size outdoor unit that's housing the fan and the refrigerant lines. The other thing that's exciting is, so let's just hop back real quick. So these types of technologies, these were originally all developed in Asia. They've been around for over 50 years. But over in America, we have been using a type of heat pump for a really, really long time, and that's central AC. So central AC works the same exact way a traditional heat pump works, but it only goes one way. It just takes the heat from inside the house, passes it over a really cold coil, brings that cold refrigerant to the outside, compresses it, makes it super duper hot, releases it to the outside. So those have been the traditional like American systems, but recently there's been a lot of synergy on the market where the Asian manufacturers are making more and more kind of like American style equipment, like those central furnaces, central heat pumps that look like furnaces, but the American and European manufacturers are now adopting a lot of the same type of technology. So like inverter-driven, cold climate, central air source heat pumps are now market ready, widely available, and provide zero compromises. So here we're just looking at a few of these, and what's exciting, this product category would be called the unitary heat pump. So 1 unit outside, 1 unit down in the basement. What's so cool about these systems is they can be integrated with traditional hydronic systems as having a gas backup. So there is a lot of, there's still a lot of concern about the marketplace, about heat pumps, about it being new technology. But the really exciting thing that I feel about these, American and European manufacturers is, if you just feel like you do want the additional complexity - redundancy of knowing that you can still run gas, that if there is ever like a snowpocalypse and the outdoor unit's buried in snow, you could still have gas tied over to your distribution system. These types of heat pumps can accept hydronic coils, they can have electric resistance, they're extremely flexible, they're not quite as efficient as what we'd see from a Fujitsu, Mitsubishi, or Daikin, but they're a huge step in the right direction from doing what we've always done. So this one comes up probably more than any other question. How much are they? Are they affordable? And it's really complicated. So in Massachusetts, we're constantly ranked best in the nation for energy efficiency. And we have a lot of programs that are supporting the adoption of electrifying our heating and cooling. So Mass Save has some great rebates for oil, propane, electric resistance customers. The DOER, they have the Alternative Energy Certificate program that some whole home air source heat pump projects can qualify for. And the Massachusetts Clean Energy Center is doing some innovative things, always with heat pumps they have for the last like 5 years. They're going to be rolling out a new decarbonization program likely in the new year. So there's money that's out there. It does require someone who's kind of able to tie all these things together, and I'm happy to have those conversations. So that's what's going on at the statewide level. Slightly lower on that is 2 companies to keep in mind. So Clear Result, they kind of oversee the Mass Save program. They're the program coordinator for it. They oversee the heat loan department. If you call the main 1-800 number, they're the one who sends out the energy auditor. They're the ones who are kind of processing all of the rebates for this equipment. That's all for like retrofit. But if you are looking at doing a renovation of your home, then ICF is the company who kind of coordinates that facet of your project, whether it's, you know, continuous installation or the adoption of air source heat pumps. So sometimes when people are pursuing these projects, there's a lot of different organizations, there's a lot of different coordination, there's a lot of hand-holding that needs to kind of go on between you, the installer, and, you know, 5 different organizations that may be having a stake in your project. But the good thing is it really does, when you are able to navigate it, it really does make it affordable and to adopt heat pumps. The other thing, independent of that, is are they affordable? It depends what you want. It depends what you need. It depends the setup of the home. So as I said before, there's nothing wrong with using a large air source heat pump the same way you would a pellet stove. Most people aren't going for that. Most people are wanting, you know, to stick one in each and every bedroom. After learning about it, I think people decide that's not a good idea and they end up somewhere in between. But just know that a heat pump project, you know, could be $6,000 for, you know, this home in this zone in this footprint, or it could be $22,000, $30,000. You know, it depends what you're looking for, and it depends what your need, and it depends, hopefully, you know, what the best building science says. Now, this is probably another question that comes up a lot, and this question has been answered. It's been answered for about 10 years now, since like one manufacturer introduced like hyperheat units. But can a heat pump really be used in our climate? And the answer is yes, 100%. They have equipment today that gets down to 5 degrees with virtually 0 capacity drop. There is still pieces of equipment on the market today, like the European and American manufacturers, that do lose capacity as it drops. But it's fine, because with those pieces of equipment, they are all dual fuel. You can still tie them into hydronics. You can use them as electric resistance, or you could just have them sitting on top of a traditional gas furnace. And if you do look at the equipment and you do have it sized correctly, you'll find out with those bigger unitary heat pumps that the cutoff point on when the heat pump capacity won't be able to keep up, it's below freezing. And at that point, as we'll soon talk about, the coefficient of performance of the heat pump has already kind of dropped. So it may not be the worst thing, both climate-wise and dollar-wise, to not be using the heat pump at those low temperatures today. So just because the heat pump does have a capacity drop-off doesn't mean that it's not a great piece of equipment, that it won't save you significantly, and it won't help our environment. It's simply not true. Those are really good pieces of equipment. They just need to be designed right, and there does need to be some sort of a control strategy. With the truly cold climate air source heat pumps, the one with no capacity drop-off, 0 problems with designing 100% of the building's load, even for the coldest day of the year. A lot of the equipment still has plenty of capacity down to, you know, -10 degrees. And one thing that is important to know is when like those capacity numbers when the home's capacity surpasses the heat pump's capacity, it's not like anything catastrophic happens. If you have the heat to 70 degrees, and the heat pump can't keep up, your house doesn't become 35 degrees. It becomes 69 degrees or 68 degrees or 67 degrees. Oh, and now the sun's shining, and now it's 68 degrees, 69, 70 degrees. Like there could be, you know, if you are sizing the system really close to the building's design load, nothing horrendous is ever going to happen with it. We do need to be conscientious about whether or not it does make sense to have like redundant systems and things around that nature. But yeah, it works. There's nothing to be scared about. It's a piece of mechanical equipment. It's designed, it's engineered, it's tested, and it works. And it's what a very good amount of the world is using and is going to be using, because we do need it to meet our climate goals. The other balance point to be keeping in mind with, it's called the economic balance point. And I just pulled this. So this is with like, electricity at 23 cents. It's at oil at $3. It's at gas at $1.40 a therm. Propane, I put it at, I think it was $3.50. But not too many people in Cambridge are using propane, so we don't need to worry too much about that. But as far as where the heat pump goes, and what can you imagine to save and things around that nature, it depends. It's definitely a lot cheaper than home heating oil, and it usually is. Just this over the past year, though, home heating oil dropped all the way down to like $1.80 a gallon. At that point, a heat pump's not going to save you any money. But traditionally, home heating oil in New England for the last 10 years has been closer to $3 to $4 a gallon. And at that point, yeah, a heat pump's going to save you a bunch of money. Gas is cheap right now. It's hard to imagine that it'll be as cheap as it is today next year. Right now on the electricity side, we're paying for, when you pay your electric bill to Eversource, you're paying for EV charging, you're paying for the Mass CEC program, you're paying for the Mass Save program, like all of those things that make New England or Massachusetts #1 in energy efficiency, those fees are all tacked on to the electric bill. At some point, that's likely going to need to be changing, and gas is going to need to also, pick up its load. So yeah, as far as dollars and cents wise, heat pumps only make sense because they're today, if sized correctly, have 30 to 40% less emissions than natural gas, and they can be comparable in cost to natural gas when buying the electricity from the grid. But we'll revisit that in just a little bit. So if we do go back to, say, the heat pump in the outdoor unit was having 0-degree refrigerant and 30-degree air, if we go and look at this chart right over here, when that happens, that heat pump is going to be running at a coefficient of performance of 3 degrees. But say if the air outside is only 7 degrees, so between 0-degree refrigerant and 7-degree outdoor air, it can only pick up 7, like the difference between the two is a delta 7 versus a delta 30. So for the heat pump to be able to turn that 7-degree difference and still get that 100-degree refrigerant into your home, it's going to need to work a lot harder. And when it works a lot harder, the coefficient of performance drops. So this is something to be keeping in mind, especially if you are going to be adopting air source heat pumps and you are leaving an existing system down in the basement, or you are looking at a dual fuel setup, that there may be a point where for carbon or for dollars that it does make sense below, say, 25 degrees to let the heat pump, go to sleep and use those traditional types of systems. It's definitely not required. And if you do head in that direction, then maybe the coefficient of performance of your heat pump system over the course of the year will be like a 3.3 versus what it is if all that you do is run the air source heat pump as your sole source of heat and it's properly designed, it's like a 2.8. So it's something to think about. It's not something you need to do, but it is a truth about the technology. So what is the impact of adopting heat pumps today? So I have a little example of a home over here, just so we can all kind of really get a firm idea of what this all looks like numbers wise. So this home, it's a 2,300 square foot home. Every surface is covered with R10 insulation, which is about 3 inches of fiberglass. So the windows, the doors, the walls, the ceiling, the basement, everything, R10 across the board. And if we were to go and stick that into this equation, so the area of all the exterior surfaces times the U factor to the number of heating degree days, and we multiply that by 24, we would find out that over the course of the year, there would be about 70 million BTUs that would need to be replaced. So 70 million BTUs has left the home, we're going to need to replace that. And if we were going to be adopting If we're going to be adopting heat pumps or gas or propane, we could see how much that costs. Let's see where we are. How much that costs for 1 year of heating and how many pounds of CO2 equivalents would be released into the atmosphere. And one of the things that I do want to highlight is I did put a poor performing, or I should have wrote a poor designed air source heat pump that will have a coefficient of performance of 1.7, and a well-designed air source heat pump will have a coefficient of performance of 2.8. And when we plug in all those numbers, oh, sorry, there's a tiny typo. So the red is going to be cost and the white is going to be emissions. So when we plug in all those numbers and we look at how much this is going to cost over the course of 20 years, a natural gas furnace or boiler would cost about $20,000. And over the lifespan of the system, it would be producing just shy of 80 metric tons of CO2 equivalents. And if we look at propane, a lot more expensive to run, definitely some more emissions. We look at home heating oil. At this point, it's nearing up twice as much to run and significantly more emissions. And electric resistance, we'll revisit that today, but we don't want to be heating solely with electric resistance. This is what I want to focus on, that poor performing air source heat pump, which gets installed all the time, but it's 100% preventable. It's going to cost likely more than home heating oil. It's going to produce nearly as much emissions of home heating oil. There's no carbon benefit of switching over to an air source heat pump today if it's not sized correctly, if you're trying to beat out natural gas. But the well-designed air source heat pump, yes, it does cost a bit more over the lifespan of the system if all the fuel prices are locked into place today, but the emissions about 40% less. Now, this is exciting for anyone who's involved in, high performance or is environmentally minded, is every single year our grid is getting cleaner and cleaner and cleaner and cleaner. And we have, by 2050, hopefully the problem is solved. Hopefully we have enough renewables on the grid that we're no longer worrying about, any of these emissions coming off of it. But it's going to take a long time for, Eversource and National Grid and ISO New England to get this all figured out. We've tried to do big wind projects, off of the Cape. It looks like we may be getting a lot more wind power in the very near future, but there's a lot of things to figure out to make this happen. And I hope that it will. The good news is that today, with on-site renewables, it is so unbelievably affordable, and Cambridge is doing really good things with trying to support the residents through Sunny Cambridge. So just to put this in perspective of how much solar PV cost has dropped. In 2008, it cost $8 per watt. In 2018, that number got cut in half. But today, like literally today, if you go on Tesla's website, you can buy PV at $2 a watt. If you're going with, if you're working with local installers who will provide a lot better customer service, handholding, and likely support if something does go awry, pretty much most projects are coming in right around $3 a watt. And federal tax credits here, the SMART programs here in Cambridge, state tax credits. So a lot of different ways to be making that affordable. And what ends up happening if you go and look at the 20-year cost. So if you're sizing a solar system to meet your heat pump system, I'm more than happy to talk to anyone about how to actually do this. If you're, instead of paying for that 20 years worth of electricity, you're buying the solar PV at $2 a watt, what ends up happening is you end up with generating all of your heatings through your air source heat pumps tied to renewables. You're not releasing any CO2 equivalents anymore into the atmosphere with being tied over to the grid. I know there's different definitions of net zero, but this feels pretty darn right to me. Even with a poorly performing air source heat pump, it's going to then become priced competitively to natural gas. But that well-designed air source heat pump, it's going to, be significantly cheaper than it would be to just be buying natural gas from the utilities. Zero emissions. It's 100% possible. I'm doing it for my home. A lot of other people, I didn't come up with this idea. A lot of people are doing it. This is really kind of the dream. And it really is achievable. I know Cambridge has a lot of complexities with roof space and different, renters, condos, multifamilies, but this is really worth pursuing because it really is the way to be most impactful about how your home is using energy. So how do I think about design? I've talked a lot already about like a poorly designed system and a well-designed system, but this is how I think about design. So we have that same home. So the overall R value or U factor, just the inverse times the outdoor area. And then you times that by the difference of temperature between what you want the thermostat set to, 70 degrees, and the outdoor design temperature, which in Cambridge is about 12 degrees. You multiply those two things together and it'll give you a number. So in this case, it's about 30,000 BTUs. This is how old timers used to do it. But now there's really robust software called the Manual J, and you take measurements of all your windows, all of your walls, the height, the insulation, the shading, the U factor and the glazings, and it pulls together, if the installer does it correctly, a room by room exact measurement of how much heat is going to be needed to keep it at temperature and how much cooling and humidity removal is going to be required in the summertime to keep that room comfortable. And that's called the Manual J report, and it's so important. So we're going to be dealing with a Manual J of 30,000 BTUs. And this is the marketing material, and this is what a lot of ductless installers talk about. We'll put one in each and every bedroom, one in the living space, one in the living room, one in the kitchen. And say if you have a house that needs 30,000 BTUs, and you put in this piece of equipment, so you need 7 indoor units. The only piece of equipment on the market right now that can take 7 pieces of indoor equipment, it's a 4-ton system. And this is what ends up happening. So this is all the weather data over the course of the year. So the high temperature as well as the low temperature, and you see that over in blue. And then the orange line is going to be the average. And on the left-hand side over here, we have the outdoor temperature and how many BTUs the house needs. So we're in Worcester. So at 0 degrees, this house needs about 30,000 BTUs. The piece of outdoor equipment, because we want 7 indoor equipments, it's a 4-ton piece of equipment. So when we put that in this home, this is going to be the range that it's going to be modulating. So this has enough capacity between 27,000 BTUs and 56,000 BTUs. On the coldest of cold days, yes, this system's going to be modulating. It's going to be working efficiently. It's going to have enough heat no matter what solar vortexes throw at it. But pretty much every single day in the winter, this system is going to be oversized. Every single day in the spring, summer, fall, 100% oversized. So this is the problem with the traditional design with ductless. I have a radiator in this room, I want a ductless unit in it. We need to think a lot more critically about it. So let's just say that we do size the system down. So we go and we put in, we see that the load is 30,000. The closest piece of outdoor equipment to match the load is a 2.5-ton system, and this will range from 11,000 all the way to 28,000. And you look at this and it's like, great, I got the majority of, I got all the winter, I got, a good chunk of the fall, a good chunk of the spring. This is working a lot better. But the problem is if you are designing air source heat pumps to meet 100% of the design load and you're gonna have no additional equipment down in the basement, you can't do it. They won't sign off on it. The equipment load doesn't match the home's load. You're gonna run into a problem with the inspector. So you're gonna now need to size up the equipment. But so once you size it up from that 2.5-ton system to a 3-ton system, we're kind of right back where we were. We're now missing pretty much the majority of the winter, all of the fall, and all of the spring. So one of the things, if we do hop back just to this section over here, there's ways to bring down your load from 30,000 to 28,600 BTUs. So change up some windows, air seal your house, lower the infiltration, get your attic past 6 inches of insulation. It should have about 15 inches of insulation up there. Seal around your room joists. There's ways to work with this piece of equipment without needing to select different equipment. I just wanted to highlight this. But this is really what we want to see. This is the gospel that we're preaching to anyone that we can talk to, if it's contractors, customers. Instead of just working with this one big piece of outdoor equipment, break it up. So if you just put in a single zone piece of equipment, that piece of equipment can modulate from 4,000 BTUs all the way up to 1.5 tons. And then for all the bedrooms, use a ducted piece of equipment, which is going from 8,000 to another 1.5 tons. So you have 2.5 tons pieces of equipment. When you have those two pieces of equipment working, you're covering 100% of the load. You're not missing anything. You're not like missing any. You're not missing any opportunity for the equipment to modulate. These are the systems that have coefficients of performance in our area very, very close to 3. These are what keeps it cost competitive to natural gas. These are the ones that have 40% reduction in CO2 equivalents. So I just really want this to hopefully be the takeaway from anyone who's watching today. The last thing that I wanted to talk about is that, I know a lot about this stuff, and there's a lot of information out there. Some of it's older, some of it's outdated. It's really hard to tie solar and heat pumps and solar hot water and on-site renewables and on-site energy storage, and how do I integrate any or all of this into my business? So a resource that the City of Cambridge we wanted to make available for you guys is a series of courses. It's called Start Smart. It's a training that we did primarily for new construction professionals. It's done on behalf of the Clean Energy Center. We worked with a lot of HERS raters, architects, builders, the top installers we could find in the region to really talk in depth about all of these clean heating, cooling, and renewable energy technologies. So it's a really good course pack. It's all videos. Each video is about an hour long. There's 6 different technologies that got highlighted. We really did try our best to figure out who the best people in the marketplace, who really were the subject matter experts in each of these to, tell builders, tell contractors, what is important about these technologies, how they can get adopted. And I think we did a really good job, and the feedback that we've gotten on it's really good. The other incentive, instead of just getting smarter about all of these things, we did get this course approved through the state. So if there is any people who do have a construction supervisor license, where you need 18 CEUs over the course of your before it expires, this course provides 6 CEUs to you in the energy category. So it should take off a good chunk of the burden. The City of Cambridge is covering 75% of the cost. And if you do want to get a unique promo code for the course, just head over to abodeem.com /chat, and you can create a meeting with me. I'll talk to you about heat pumps, talk to you about solar, talk to you about solar thermal. I'll tell you how to access the course, provide you with a unique code, and all of this, all of that consultations at no cost. We welcome your input and feedback. I know a lot of times if you are working, one of your customers is working with me on a project, I'll be providing a lot of feedback, I may be providing suggestions or criticism as far as design go, but we do really want to establish a working relationship with every contractor who's working in the city, whether or not it's whether it's to fix a leak or save the planet. We're here to support you, and we're here to help you kind of understand exactly the lens that the city is looking at its buildings as far as where they need to go. And I'm happy to spend as much time as possible with you to, help, hold your hand and get you to where we all need to go. It was a real pleasure to speak with you today. And if there's any questions, I would be happy to hear them and take them now. All right. Thanks a lot. And Ryan, if you want to take it from here.